This is a demonstration video of an Analatom AN110c, a corrosion health monitoring system to measure corrosion rates and environmental conditions on high-value assets and structures. The AN110c is a ruggedized, field-grade, waterproof potentiostat with 8 channels of information, 4 on each side, for corrosion rate, time of wetness, and salinity information. On the front, along the top row, there's the Zigbee wireless interface, relative humidity and temperature sensor connector, RS-45 serial interface connector. On the bottom row, left to right, the external voltage input. It's optional, from 5 to 30 volts DC, another RS-45 connector, and an RS-232 serial interface connector. The unit runs off an internal battery with a battery life typically of 7 to 10 years. The demonstration today will consist of 2 corrosion sensors under a protective coating on a metal plate. The corrosion sensor's channel 1 goes to channel 1 of the unit. Second corrosion sensor goes to channel 2 of the unit. I've placed corrosion sensors on top to show where they are, but actually they're underneath the coatings and they're not so visible. So I'll remove the sensors just to show where the actual sensors are. And here is the relative humidity and temperature sensor between the two to record environmental conditions, although the sensor itself can be placed anywhere deemed proper by the domain experts who are doing the structural monitoring. On the screen, it shows the CMAS host user interface software. In this case, it's version 1.31. It's used to connect up to the unit over this, in this case, over the serial interface cable, and you get status and condition information back from the unit uploaded to the host. The unit has enough flash memory to record up to 5 years of sensor data. Typically, you use the unit in 2 modes. In the remote mode, the host would start the unit and then disconnect from the unit and allow the unit to sample the sensor suite at the user's selected sample period, which can be from once per minute to once per day. Typically, for corrosion applications, it's once every 60 minutes, although it can be, for a little more information, the sample period can be selected as 15 minutes or 30 minutes or 20 minutes. But typically it's an hour, every 60 minutes. In this case, for the demo, we're going to go into real-time mode. That's different from remote monitoring, where the system is recording and storing the data by itself in a remote application. This is in real-time mode, so every so often the system will send the sensor suite information back to the host. I've selected a sample period of 1 minute, and for all sensors, and we're going to enter real-time mode. The real-time data acquisition window comes up, and since we only have 2 sensors connected, we're going to look at channel 1 on graph 1, which is the intact coating with the sensor underneath, and channel 2 also in graph 1, which is the sensor underneath the defective coating. And we're going to select corrosion rates. We're going to look at the corrosion rate itself, the instantaneous corrosion rate itself, in grams per square centimeter per year, uniform surface loss. Typically, in a dry condition such as it is now, the corrosion rates under both sensors will be 0. And for environmental information, I'm going to add the external temperature. We'll put that in graph 2, and the relative humidity, which is measured in the presence of the sensors. So here in the room, the relative humidity is approximately about 56%, and the temperature is about 20 degrees C. Again, the corrosion rates are 0. I'll let it record, since it's sampling once per minute, I will let it record 1 more sample period. And then we'll add some electrolyte, which will be simple tap water, which will penetrate the defective coating and start an electrochemical activity corrosion around sensor number 2, and the intact coating will show much less corrosion, practically 0. Okay, we have 2 samples where both corrosion rate 0. Now we're going to add some electrolyte in the vicinity of both corrosion rate sensor number 1 and number 2, and the relative humidity and temperature sensor. Again, here's the intact coating under channel number 1, and the defective coating right above which sensor number 2 is underneath, and the relative humidity and temperature sensor. All sensors can be placed on 5-meter cables, such as surrounding the relative humidity and temperature sensor right now. And the sensors themselves are linear polarization resistant sensors. They're small, they're thin, they can be placed under sealants, coatings, protective coatings, or in hard to access areas on your structure. And an advantage of our system over the competition is our sensors are fabricated from the same material as the structure, so they exactly emulate the structure. In an aerospace application, the sensor will be fabricated from aerospace aluminum alloy, and for bridges and pipelines and other structures, it will be fabricated from low carbon steel, which it is in this case. So as we can see on the screen, the electrolyte has penetrated the defective coating. Channel number 1, which is the sensor under the intact coating, corrosion rate stays relatively 0, and it's greatly increased under sensor number 2. The sensors have a very quick response time, and they're very sensitive. And as you can see, in the vicinity of the sensor, because we've added moisture, the relative humidity has increased. And although it's harder to see, the temperature has actually decreased slightly because of evaporative effects in the vicinity of the sensor. Again, as more electrolyte penetrates the defective coating, the corrosion rate is increasing under sensor number 2, channel 2. And as time goes by and the electrolyte evaporates, the corrosion rate detected by channel 2, sensor 2, will start to decrease and come on back down to sensor number 1, which is the sensor under the protective coating, which is seeing minimal electrolyte intrusion. So this is to give you an example of how the system works with the host software and the sensors, their installation, and the AN110 unit. So to end the demo, I'm going to stop the real-time monitoring. The system, the host software asks, do you want to save it? Do you want to save the data? You can save it in a proprietary format for the corrosion health monitoring systems, but you can also save it in Excel format, comma separated variable, or text format. In this case, I'm not going to save it. That's just the typical usage of the AN110c system. In a typical application, you'd be monitoring remotely. This unit has been used on aircraft, has been used in bridge suspension cables to monitor the corrosion rate inside the suspension cables. It's been used on buildings. It's been used on warehouse roofs in subtropical areas. So it has a very wide applicability. It can be used on virtually any infrastructure for monitoring and recording the corrosion rates and environmental information and reporting back to the host.